We're back recording, everybody. Let's get ready to rock and roll here. All that kind of good stuff. Where's my muse? Would be the way to describe it. It's all right. I've already been with a one roommate in the morning, so it's like a double header of those. Oh my goodness. Now, moving on. So I briefly just want to do a little highlight film on the cell from my perspective. We're not redoing cell molecular. I'm not going to sit there and ask you what the mitochondria does or that kind of nonsense. But we did the first two. And I mean, really, as soon as we finish with this, and we'll surely get it, if not done today, then done by Wednesday, we get into the muscle phys and things start to get very active and interesting. So, well, I mean, so this is just talking about the cell and all the organelles and all that stuff. To me, the most interesting thing, and it's a continuing factor, is to understand, from micro, you surely got endosymbiotic theory, is the idea that we're dealing with its own DNA, just like chloroplasts have, and its own RNA. This is 70S RNA and basically prokaryotic DNA, a single circle of double-stranded DNA, and the fact that you can make if you're on a workout program, you're going to increase your muscle mass, you're going to make more mitochondria. If you're injured and you stop for whatever reason, or you just choose not to do it anymore, the mitochondria will begin to disappear and not be replicated once they're effectively no longer useful, because they're an organelle with a lifespan. So we have the luxury of making more when necessary. So the capability of fission and the fact its resemblance to prokaryotic structure, cell structure, and prokaryote, and really that's the crux of endosymbiotic theory, which plays a very important role in justifying evolution. Even though that's not something that I teach about evolutionary biology. The other is, if you're going into a health-related field, or they give you an antibiotic, the reason you have side effects with certain antibiotics, the vast majority of antibiotics target two structures. The cell wall, penicillin, cephalosporins, the most commonly prescribed. If you're allergic to those, things like the Z-Pak, basically they target ribosomes. And the problem with targeting ribosomes is they're targeting the 70S ribosomes within the mitochondria. That's where side effects come from. So it's where the allergies are much more about the cell. Well, it doesn't preclude allergies or side effects on other side. It's just the commonality of it. And we don't have to go look at pictures. And the difference between free and bound ribosomes, you do that in cell and molecular. What makes it bound. And, basically, the whole idea is if it's going to be a bound ribosome, the proteins are going to be used in one of only three possibilities, three pathways. They can either be within a membrane-bound organelle, like a lysosome or peroxisome. So they're going to be membrane-bound but kept within the cell. They're going to be membrane-bound and put in the membrane itself as a membrane protein, or they're going to be in a secretory vesicle and excreted. It's three pathways for bound ribosomes. And the free ribosomes are everything else. All the other proteins, the neat little microtubules and microfilaments, da-da. And so they're going over all that. So I'm as you can see, when I rush through things like this, one, I don't think it's necessarily testable material, or if it is, it's something you guys have already had 63 times. How many times have you had the cell? And your nuclear pores, the whole so this is basically the endomembrane system 101, continuous strand of membrane-bound structures that are effectively continuous in the sense that the pores lead into the rough and smooth endoplasmic reticulum in all cells. And why do we have it? Because it's protective in nature. The inside of a cell is harsh. Chemicals everywhere, areas with more acidity, areas with less acidity. So things that we don't want to denature or disrupt, we maintain them in this. It's just basically, it's almost like a sterile corridor, if you want to see it. I used to use the analogy down in Baltimore is, if you ever go to the aquarium there, it's like a walkthrough. You're like in a glass walkthrough with sharks swimming around you and stuff like that. The Inner Harbor, if you haven't been to Baltimore, is great. And the food scene is great. Crab cakes, pit beef. That's where, if you did not know, that's where Steak Diane was originated. Went to that restaurant. I digress. Okay. Other than the fact that they have ravens and had Orioles, still have Orioles. So the protein cisterns, Golgi, fluid filled. So when you see cells rich in rough endoplasmic reticulum, they're making proteins mostly for export. Pancreas, insulin, anything where you're going to make a lot of those. The flip side is the smooth endoplasmic reticulum. That's what you see an abundance of in the liver. The reason is fat detoxification, which are mostly fat soluble, a whole lot of basically the metabolism and the utilization of fats, all parts of that, and obviously the glycogen aspect. And as you're going to see when you get to muscle, we're going to start looking at variations of the smooth endoplasmic reticulum within muscle cells called sarcoplasmic reticulum, and that's critical to the understanding of muscle physiology. It is extraordinarily important. So all of that. So it's mostly, there's a little bit in smooth, but mostly smooth is sort of an oddball, but cardiac and skeletal muscle. And our focus points are going to be skeletal and cardiac, and to a lesser extent, smooth. The Golgi, nothing more than a processing, packaging, and shipping center, effectively modifying these proteins for wherever they're going into, whatever the appropriate form is. And again, most of it's covered in cell and molecular, and effectively just a series of vesicular passageways assisted by motor proteins. You know, the whole cis and trans end, which we're not going to talk about, and all that. Neat pictures, love them. And here are the three pathways, either secretory in nature for exocytosis. We're going to talk about neurotransmitters very soon ad nauseum, containing lipids for transmembrane proteins within the plasma protein, and lysosomes and their cousins, the peroxisomes, which are both of significant importance in our eukaryotic cells. There, voila, voila, see it moving around, happy dance. The peroxisome, the critical piece for aerobic organisms. We only see them in aerobic organisms because it's there that they're dealing with the toxic derivatives of oxygen. Okay, so you have all oxygen. What's oxygen's number one? It's the terminal electron acceptor. Effectively, we bombard oxygen with electrons, and periodic. Now, most of the time, we get O-2. We get a couple of protons from the proton motive force, and the two protons and one oxygen get together, and voila, we got water. And happy dance. But unfortunately, oxygen, for the most part, periodically forms that O2 with a minus sign called superoxide radical. That's the worst of the free radicals. And free radicals are like any structure, they basically attack stable structures and destabilize them. So they bump into other compounds and create more and more free radicals. And I'm sure you've had it. So they're highly reactive. We can't avoid them. That's why we have peroxisomes. Peroxisomes have at a minimum two enzymes. You've all had this before, I'm guessing, superoxide dismutase and catalase, right? You all did the bubble test with catalase. Hey, effectively what happens when in a wound, we cut those, and the peroxisomes, they're disrupted, they release the catalase, peroxide gets put on it, it rapidly converts peroxide to water and oxygen gas. So effectively it oxygenates the wound. And a lot of bacteria don't tolerate high levels of oxygen because they have limited mechanisms to deal with that higher oxygen environment. The superoxide dismutase takes that O2 with a minus sign, and stepwise, without drawing, and you can look up the chemistry behind it, the O2 minus to peroxide, which is also a free radical, good old hydrogen peroxide, and then the next step is the catalase takes the hydrogen peroxide and get rapidly to water and oxygen gas. That's why it bubbles. Peroxide on intact skin, no bubbles. Peroxide on damaged skin, bubbles, burns, all that, quick transition. And yeah, there's some role in fatty acids I'm not that familiar with. So lysosomes, again, anything that we bring into the cell, other than for transcytosis, where it's just transiting through the cell and has no interaction has to be addressed by a lysosome. So you have some kind of endosome called a phagosome, generically, fused with the lysosome. This is the way we've been doing business forever. It's macrophage 101. Phagosome, phagolysosome, gobbles it up, digestion and defense. So it either digests the particles to some extent so we can use them as nutrients, or it destroys them if they're bad guys, for the most part. The big problem is when we end up with materials that are either not destroyed or they set up shop within a lysosome, like tuberculosis, for instance. Okay, they hijack that mechanism to a certain extent. All of those are part of it. Yes, they play an additional role. We talked about in anatomy with bone. Okay, and we see a lot of them, and really they're that so-called like suicide pack thing. When we hear about autolysis or we hear about apoptosis, it's basically lysosomes popping, sort of like what's his name, Dr. Kavorchik, guy up in yes, ma'am. Hi. I was saying hi before. Oh, okay, I didn't know. I look. This is my day. I get 2 classes with you and 1 with Chelsea. What would be better? Right. I mean, other than maybe a mutton, lettuce, and tomato sandwich where the mutton is sliced very lean. An MLT. An MLT. Princess Bride. Right. I've seen that movie. Have fun storming the castle. Name is Inigo Montoya. You killed my father. Prepare to die. The great Mandy Patinkin in his early days. Oh, God. He is a real pain if you did not know to work with. He is intolerant. Doesn't play well with others. He does not. He's very intolerant. Moving on. So you did all that. Lysis, I talked about Tay-Sachs disease, right? Everybody, very significant. And effectively, it's particularly so. And like I said, this was one of the early things that we were testing. It was sort of a dreaded thing. There's a lot now. It's interesting. It's sort of generically speaking. There's so many more tests that are available as part of genetic counseling. Genetic counseling was in its infancy. There was a guy down at McGee in 1980 with my first wife named Ken Garber, who was one of the early genetic counselors. I mean, it's just not that 43 years is not that terribly long time. We underwent that, and there was a lot of early work done in that. And it was very, very fascinating. The endomembrane system, again, just this continuum, starting at the nuclear membrane, effectively going to the plasma membrane through all those structures that were detailed before. The intricacy of the human cell. I'll send you the link so you can watch it rather than utilize clip, because maybe you've seen it. Have you seen that Harvard animation? That most of the time you have seen that at some juncture in school. They did it about 2000, about 20 plus years ago, where you started to see their concept of how the cell membrane was, and we see it even in our animations. It's very similar to what they use here. And that one focused a little bit on how white blood cells left blood vessels, alterations, why there's marginalization, chemicals that cause internal proteins to change configuration, latch onto white cells, which move slower than red cells anyway, so they're closer to the edges of the blood vessel, to the capillary itself, get latched onto subtle changes there that allow it to be, so they can change, they can sort of squeeze through little nooks and crannies, which a lot of cells can't do. So they kind of like that, they can sort of shift their way like when a door is only partially open and stuck, you kind of go sideways through it. And they're able to do that, all because of chemicals. So if you don't, I'll send you the link. I just always Google Harvard cell animation, and they have it with music. They have it at different speeds, and I'm sure they have it on YouTube. You can surely find it if you want to look at it. I used to do that all the classes, but it's easy nowadays. It's so much easier for you to do it on your own rather than have to incorporate it. It's there. And then again, in order of size, from smallest by diameter to largest, microfilaments, intermediate filaments, and microtubules. Most significant factor, microfilaments, Microtubules are individually, when they're assembled, they're insoluble, but they can disassemble and reform anywhere. It's just like during mitosis with the spindle. Those are microtubules. During amoeboid motion, the microfilaments assemble and disassemble. Okay, so it's almost as though the cell, and it's conserved. So you have one part of the cell that's here, and if you think of amoeboid motion and the idea like a baby scooching around, it's almost like they're disassembling on one side and they're assembling the other side, pushing the flexible membrane. The cytoplasm flows, and sort of it's like after a tough night, you know, probably the Buffalo Bills fans, they're on the floor in tears. That was so sad. The one guy was just, it's horrible. Pardon me? Yeah, like the pseudopods. So they form pseudopods and it kind of scooches around, which is just fascinating, I think. So they are inherent when they're assembled, insoluble, when they're individualized and disassembled as to the little, and we're going to talk about that. Globular actin, which makes the microfilaments, when it comes together, it becomes F, or filamentous actin. And the microtubules are the same thing. It's like assembling and disassembling a spindle for mitosis, which we're going to go over soon. And the oddball, and the one that's interesting in the fact that it's always insoluble, are the intermediate filaments. They're intermediate, so they're between the other two, and they're insoluble. And that's what holds cells together. When we did skin, and we did all those layers of skin, and you got the stratum spinosum, what made those cells appear spiny might have been the way they were prepared for looking under a microscope, but to some extent, it was those junctions, the desmosomes, holding on to them. And as they enlarged, you began to what appeared, at least microscopically, to be little points. So the microfilaments, actin, okay, unique arrangements, okay, on the cytoplasmic side, as we're talking about in the plasma membrane, they're very useful because they resist compression, very significant in endo and exocytosis. So the name is going to come to me. Early medicines that were anti-metabolites, that had a lot of side effects, really stopped some of these processes with either microtubules or microfilaments. And the trouble is they were sort of universal, so they had a lot of side effects. They were like early anti-inflammatory agents that were used way back. So I remember I got my prescription pad in 1977. I know. I keep saying these numbers. Not that funny, young lady. Why do I get this abuse?
It's a great year.
What?
It's a good year.
I know. So here they are. And you're going to see this configuration a lot when we get to muscle, that double string of pearls kind of a look. It's really important. We start to look at muscle physiology. I know you've had it. We're going to really explore it in detail with the troponins and the tropomyosin, the actin filaments, and the sliding filament theory, which is how muscle works. Intermediate filaments, they're tough. Tetramers generally. We do we've mimicked that for years surgically. We take monofilament and we braid it. So in surgery, we would take, in the old days, when they didn't have a lot of stuff, we would take monofilament steel wire and have basically create two ends. The end that had the little, had the hook on it, as it were, the needle, which is typically curved. And someone would hold that in a hemostat, someone would hold the other end of the hemostat, and we do the twist. And we braid it. We effectively create a braid, which is what a tetramer is. And we'd use that to wire bones together. Drill holes in the bone, pass it through like a steel suture, twist it some more, clamp it down, bury it inside the bone. Happy dance. So that's how we would fixate osteotomies or fixate fractures. There were different wiring techniques called hemicerclage and cerclage wire techniques. So we twist them together. And so your body does this naturally. That whole, we get, again, how many times will I talk about the pleating thing? In proteins and pleated sheets, effectively creating all this abundance of surface area that we talked about in anatomy, let's say in the gut. So we imitate that a lot of times therapeutically. And so desmosomes have plaques, internal guy wires, neurofilaments and nerve cells, the keratin filaments I was just talking about with regard to the skin cells. So here you can see this tetramer being braided, creating strength. And the microtubules, by dimension, a different protein, not actin, tubulin, okay? Coming from, not all of them, but most from that centrosome within the cell where the spindle forms, and effectively to me, these are roadways that are internal roadways where organelles are attached, where motor proteins ferry vesicles along the way, all of those things. And what's neat is you can disassemble and reassemble if you need to put the pathway in another location or additional locations or less locations based on activity. And again, it has a different kind of configuration because inherently they spiral to some extent. So they're hollow as opposed to that double strand of pearls, which is a different configuration. Changing shape and lugging stuff. Centrosome with the centrioles. I'm not going to rebuild the wheel, but they're the basis. What comes out of there are cilia and flagella, where the only flagella that we have in the human body is obviously in the sperm cell. Okay, so it's unique to the sperm cell, but cilia are everywhere. So respiratory and gut, all those wonderful pseudostratified ciliated columnar epithelia, my favorite. All those goblet cells interspersed with mucus. Love it. Here they are. And the two different configurations, again, scientifically, evolutionarily, because when we see early, the simple eukarya, the protist, the protozoans, they have the 9+0, the 9 triplets in the centriole itself or in the basal body where the attachment is of the cilia or the flagella. So you have that 9 triplets, and then when we finally see the development and we cross-section the actual cilia and flagella, now we basically see that 9+2 configuration. So the 9 doublets with the 2 in the center. So it's similar but different. And I think that's important. And again, the distinction in prokarya, when you see flagella, they basically are like a helicopter that can go in one direction or the other. Whereas in our eukaryotic cells, they're whip-like motion, like little oarsmen, they usually do in country. So there's really significant differences between eukarya and prokarya. And the reason I say this to you, if you're going to take, whether it's MCATs or the dental admission, whatever admissions test, they focus on this stuff, or GREs. So knowing that, the first thing in the question says prokarya or eukarya, you underline that. You somehow highlight it. You got to figure out where it is because it has such a different meaning. And sometimes we don't see it. Like flagella are totally different and much smaller in prokarya, even though flagella are super important in bacteria. So voila, you got all that. There it is, moving the mucus. Not going to do that. And microvilli, again, are another one of those structural things to add surface area. They were abundant, particularly in the gastrointestinal area. That massive amount of surface area in the small intestine is remarkable. It's not the only area where we have it, but those are actin microfilaments that play a role. So you can see it's that sort of like magic fingers that just create this abundance of surface area. And when we get to it, you'll see in the physiology portion, this is where brush border enzymes and such are found. And nucleus. Yeah. A typical cell obviously is one nucleus. Multinucleate cells are very, very advanced in the sense that it's a confluence of cells. And that's why when we start talking about shortly the cell cycle, why they don't necessarily apply. The liver cells notwithstanding, because the liver is sort of an unusual organ that's there. And the fact that and the only reason a red blood cell doesn't have a nucleus, it doesn't need it. It's there for formation, but then it just takes up surface area for job one for red blood cells, which is carrying oxygen. And we do a whole extensive unit on the blood, one of my favorites. And we're not going to get into the, same test question for everybody. Every class I've ever had with a nucleus, What does the nucleolus do? It makes ribosomal RNA. It's always a test question. That's always the answer. So you're guaranteed to have one right, which for some of you is important. What? Yeah, I will personally get 20 lashes with a wet noodle.
Wet noodle.
I used to have a professor who, not a professor, a high school teacher who said that, who didn't like me, but none of them liked me. And then the chromatin versus chromosomes, and I'm not, the nuclear pores, not going to do that, and all that stuff. There it is, ribosomal RNA, chromatin versus chromosomes, not going to do that. The whole, to me, it's when you see that sort of beaded appearance, the histone proteins are interesting because to me, the natural tendency for nuclear DNA in our cells is to supercoil. And those histones hold it in configuration. So there have been a lot of, vis-a-vis cancer, trying to control their ability to coil and uncoil vis-a-vis mitosis, and trying to work on histone proteins as being a possible point for intracellular cancer control. Because cancer, again, as we'll see shortly, nothing else in the cell cycle gone crazy. And the centromere, and I'm not going to go crazy with that. That was my brief view of parts of the cell. So happy that's over with. The cell cycle forthcoming. The important part. And I only do that. The remainder of this PowerPoint has a lot of cell and molecular vis-a-vis RNA and DNA assembly, those APE sites, whatever I'm not doing it. It's above my pay grade. Dr. Hillig understands it, I don't. And she's considerably brighter than I am. The cell cycle. Most important thing to understand. To give you the frame, we were taught way back in the day, before we understood molecular biology, that cells were active during mitosis and relatively quiet during interphase. It's the exact opposite. Mitosis is a limited amount for most cells unless they're highly reproductive. And basically, once it gets ready to mitose, it mitoses and then goes back to work. Interphase is where everything happens. 75 to 90% of the time, the cell's in interphase. Grows, carries on its usual activities, and while it's doing that, it's getting busy to mitose, assuming it's still capable of doing so. And that's the whole idea of differentiation. Highly differentiated cells, gut cells, skin cells, lining cells, mitose constantly. They're the ones that have the greatest reproductive rate are at the greatest risk of becoming cancers. Because all you have to do is flip that rate a little higher. The next thing you know, like any other thing, the faster you do something, the more likely you make mistakes. And when you make mistakes genetically, periodically, your body can't cope with them. We overwhelm our defense mechanisms. If you're an idiot and smoke 2 packs a day for 40 years, you're likely to get cancer. So none of you, I would wager, have smoked 2 packs a day for 40 years. Collectively. I'm not counting the wacky tobacco.
Yeah, that's good stuff. So
I have a certain amount of experience with that as well.
It's kind of like a vegetable,
I hear you.
Yeah.
It's a food group.
Yeah, it is. You need it.
It explains a lot. It's okay. The Beatles, their dentist, turned them on to something called the dreaded lysergic. George Harrison talks about autobiographically when he was alive. That he and Paul went to see, they were going to, a buddy of theirs was a dentist, and all of a sudden they were at a dinner with their wives who were their first wives, and all of a sudden he put LSD, and all of a sudden they got a lot more creative in their music. So moving on. Interphase, everything happens there. It's doing everything, and then you get the three subdivisions, which you all should know: G1, S, and G2. And the critical feature of all of these is that there are checkpoints, and the checkpoints effectively are, and this is a recurrent theme in the physiology of the human body. They're governors. Our natural state is to do things rapidly. Our heart would be more rapid than 100 beats per minute. It's governed by our autonomic nervous system. Your cell cycle would go crazy. These governors basically prevent it from going from one phase to another until certain conditions are met. Those conditions are governed by the accumulation of certain waste products, which collectively become cyclins that bond with those cyclin-dependent kinases. And every time you go from one phase to another, they're destroyed until they reaccumulate again, and we start all over again. It's the rapidity or lack thereof that really governs how rapidly a cell grows. Those are typically for highly or normally differentiated cells. When you, I beg your pardon, with relatively undifferentiated or modestly differentiated cells. Once you get to highly differentiated cells, they have developed so much that they no longer undergo mitosis. And typically those are muscle and nerve cells. And understand it's a good news, bad news thing. And I'll say this 1,000 times. The good news is, since they're out, quote unquote, out of the cell cycle, they don't become cancerous. The bad news is, if they're damaged, we can't replace them. So that's why we have heart attacks and strokes. It drives me crazy. Oh, grandma had a light stroke. What does that mean? She had a stroke, cells died. Now, the light may be relevant to how much functionality is no longer there. But if you have a heart attack, you had a mild, sometimes you have subclinical heart attacks. My mom had that diagnosis. She just about flipped when she went to the doctor. Because they send you a report on your chest X-ray, your EKG. Oh, there's evidence of a previous myocarditis. When would that happen? The fact that there's evidence doesn't mean that you experienced any remarkable signs or symptoms with regard to it. It drives you crazy. Okay, so from cell formation to cell division carries out its routine activities. How do we know it's in there? Because we don't see the significant signs of the onset of mitosis. So, and most importantly, the nuclear material assisted by those histone proteins is little threads that we sort of generically appear as chromatin. They don't have any distinctive appearance. When we know one thing, when the chromosomes appear, we're starting prophase. When they disappear, we're ending and telophase. So we'll look at the different subphases. So G1 standing for GAP1, very vigorous. Nearly everything that's being made for the next mitotic cycle is being made at that point. All of the building blocks, whatever's going to make more protein, more membrane, more organelles. The difference is what happens in S phase is, even though we're making more G's and T's and A's and C's, we're not assembling it. That's S phase for synthesis. And that, ladies and gentlemen, is where mutations occur. Definitionally, a mutation doesn't mean, we all had this with silent and nonsense and missense mutations, all those different categorizations of mutations in genetics. Well, all it means is there's an error in DNA. Whether it has anything, we make errors in DNA all the time. We make 1 billion cells easy every day. Easy. Okay. Mutation is an error in DNA. Our repair mechanisms, most notably DNA polymerase III, are able to correct that. Not only does it identify the mutation, it corrects it. It's not like in bacteria, in prokaryotic cells, where they do mismatch repair. You're as likely to. You all did that experiment with you mutated the E. coli and you put the pigment and phosphorescent pigment markers on it, right? Am I ringing a bell? You plated it out, and about half of them fluorescent, half didn't. So if you make 20 plates, it's 8 to 12, 10 to 10, 9 to 11, more or less. If you do the whole class, you always end up right about 50-50. That's mismatch repair. Our cells are wonderful. we have three different mechanisms in addition to the genetic code with all the built-in repetitive nature of that, so we are less likely to make errors. Okay, we have paired chromosomes. Okay, so we have dominant and recessive. If both are dominant and both are recessive, unless it happens specifically, the mutation occurs on the one that's expressed, and if it happens on the recessive in a heterozygote, okay, who cares? Tree, forest, make a sound, don't care. That's great. So we have pairs of chromosomes. We have the aforementioned DNA polymerase 3, and then we have messenger RNA processing. Those three mechanisms alone make it maybe 1,000 times less likely for a mutation to be of significance in a eukaryotic cell be a prokaryotic cell. It's a good thing. I'm happy to be a eukaryotic cell. I have a little placard in the car. I'm happy to be a eukaryotic organism. Why are we sending me these? Do you ever get these ones from somebody you never heard of about a package that wasn't delivered and they want your information? F you and the horse that brought you. As we say in Yiddish, num de cup and schlugen wand. You know what that means? Go take your head and bang it against the wall. Yiddish is a very good language to get people.
Every time you say something in Yiddish, you just throw syllables at us and then make up.
It sounds like syllables. It's a very harsh sounding language. Linguistically, it was Middle German with a little bit of Hebrew put in. Just in case you're wondering linguistically. Moving on. So and gap 2 are all my ducks in a row. Have I got enough of this? Have I got enough of that? Okay, good to go. Boom. Let's reproduce. Don't lie. It's not that funny. We're talking mitosis. None of that other funny stuff. And there it is. Love this. Looks like a sundial to me. The major checkpoint, G1, with the restriction checkpoint, and then the G2. So if it gets past those, it's going all the way. Okay? And so you have, again, I say it all the time, PMAT, prophase, metaphase, anaphase, telophase, cytokinesis, which begins typically in late anaphase or telophase, not hard and steady rule. It's sort of like, again, it's a balloon puppet analogy. You have a balloon, you start to give it a look, and it starts to get that crease, that cleavage fold, and in our cells, it separates rather than pop. Love balloons. Prior makes a copy of DNA. I'm not doing forks and bubbles, don't care. Okay, not primers, don't care. There's different kinds of DNA polymerase, not going crazy about it. Leading and lagging strands, and Ozaki and Okazaki fragments. I don't know which is which, never do. But you should if you're going to go on to higher levels. Okay, all that good stuff. Yeah, semi-conservative. So it's not like, it's not like a copy of a copy of a copy. I was just making some copies. You start making a copy of a copy, it begins to fade. That's the degradation. That sort of was always the knock about cloning, as opposed to our idea of semi-conservative replication, forks and bubbles, don't care. And so the control aspect is all I really have to share with you for the duration of today, is this. Without going to, okay, two things. The hallmarks of prophase, 4. You already know these? You should know them. Development of supercoiling of DNA. So we begin to see the chromosomes, number 1. The disappearance of the nuclear membrane, okay, the disappearance of the aforementioned nucleolus, and the formation of the spindle. Those are the 4 events. That's prophase. I don't care about early or late. Telophase reverses those. Chromosomes begin to disappear and become chromatin. The nucleolus reforms, 1 or 2, how many ever there are. Nuclear membrane starts to come together again. It's not like it disappeared. It sort of dismantled and reassembled itself that beauty of being able to break things down and build them back up. And the spindle begins to go back, those microtubules disassemble. That's all. So 4 events of prophase, reversed metaphase, the easiest one, they line up in the middle. Okay. And then anaphase, they pull apart, the shortest of all those. Yeah, centromeres, kinetic core, all that happens. They do early and late prophase, whatever floats your boat. About this metaphase plate, there they are, easiest, anaphase, the shortest, begins to separate the paired chromosomes, and voila, telophase, everything else reverses itself. And we begin to, with cytokinesis, is technically just the starting visualization of the cleavage furrow. Even, and again, there's some, it could be at the end of anaphase or within telophase itself, and voila. And so the signals, and this is the idea, the beauty of the cell cycle is it has a lot of controls. Cancer cells lose those controls. Contact inhibition disappears, okay, which would be a normal control for it. The formation of those cyclins and cyclin-dependent kinase units doesn't occur. And so it just begins to go faster and faster. Again, without those controls, extraordinarily fast. So surface to volume area plays a role, so the cell doesn't get too large. Certain factors will either uptick it or downtick it that are there. The contact inhibition. Again, so the regulatory procyclins accumulate during interphase, effectively they're breakdown products. Cyclin-dependent kinases form at the same time. They bond to or complex together. And every time there's been a mitotic cycle, we start the process again. Okay, and the checkpoints are all of that. Key is G1. If a cell does not pass, it enters G sub 0. So effectively, when it differentiates itself to the highest level, it will exit and go to G sub 0. That are there. And then the rest of this is all that. Exons and introns, all that good stuff, and the different kinds of, and I'm not doing it. I mean, to me, that's all basic stuff that I think you at the very least have to have a general knowledge of, though I really don't. And again, the beauty of the genetic code with, basically the redundancy that's there. And that's the whole idea between missense and nonsense and silent mutation. But generally, if it's the first 2 letters, who cares? The third letter, it might depend. Or now, if you're hitting stop codes and things, now you get problems. Bond, peptide bond. I can't think of anything else in here that's really exciting to me. But if you don't remember, again, we have a lot of this built in to remove cells. A lot of processes where we can destroy things, non-functional organelles. So it's a neat process that we're able to continually rebuild it. Okay. Again, I'm not that familiar with this pathway. I'm sure that's got to be right up Dr. Hillig's alley, right? That wasn't too bad. 5 minutes early. Downstairs, we will meet. I'll introduce lab. I'll introduce the technology. We'll get started talking about it early on. And I'll fill you in on all the lab stuff and the computer-based stuff.